Hi everyone, today we're going to look at beam design, a simply supported beam design as per the Eurocode 2. So our focus is on RCC structures. So we start this by defining a simply supported beam. And what you can tell here from figure 1 that this beam has no rigid connections. So if you look at this end and another end, it's not rigidly connected to this column or whatever you call this. It can be a column, it can be a beam, it can be a brick wall, it can be anything. So the beam is resting on it. There's no such kind of connection. And if you see this figure 2, when we talk about rigid structures that are designed to resist lateral forces, such as like if you talk about moment resisting frames, so the connections are rigid connections. So this is what we call a fixed end support. So this is a fixed end, so this is a fixed support, and this is another fixed support. That doesn't really mean simple beams don't come into pictures when we talk about RC buildings. They do come into pictures, and it really doesn't matter if we are talking about steel structures or RC structures or even timber structures. The simple beam is something that you have to learn. So understanding how to design a simple supported beam will actually help you understanding more complex designing processes of beams. Now we are designing a beam mainly to resist bending moments, shear forces, and torsional moments. We know that the architecture details often control the member sizing, okay? And usually when you are designing a beam, you'll be giving the effective span, you'll be giving the loads on this beam, and you'll be giving the materials that are being used for this design. And you will have to make up the dimensions of your beam. So that is that you have to define the B, you'll have to define the D, and there are so many things that you will have to define. But the initial trial section is not just a random guessing, it has to be logic. So when we talk about beams, we usually say that we take the span to effective depth ratio, and we will talk more about this. Well, it has to vary from 14 to 30, and based on this logic, there's also this limit for B as well. And based on this, we are ensuring that the deflection will have no issue later on when we check it. So let me just clarify this. Here's this table. You can find it on the Eurocode 2, and it says simply that the ratio L over D, the effective span to the effective depth ratio, is within this range. When I said it's from 14 to 30, so this is 14, and this is the 30. This is for the cantilever. So basically when we talk about flexural members, that is either beams or slabs, this table comes into picture. This is kind of important for us. So suppose that we are designing a simply supported beam or a simply supported slab. For now we don't need the K. We talk more about the K when we are checking the deflection. But for now we have to, well, define the L over D, okay? Because this is the first thing that you have. This is the first step that you gonna start with in the designing process. So the L over D for a simply supported beam has to be between this range. Now it is from 14 to 20. Now the thing is, here we have this highly stressed concrete, and here we have lightly stressed concrete. Usually highly stressed concrete goes for the beams, and this one goes for the slabs. So if I'm designing a beam, I have to pick up a ratio between this range, but getting closer to this tells you that you are within the beams. we'll actually have a design problem, and we'll do it from this table. We'll take the ratio from this table, and we start defining the dimensions of our beam. Right, so we move on, and let's just talk about this. Now, do we usually see rectangular sections when we talk about RC buildings? We usually don't see rectangular sections, but what we see is T sections, T and L beams. So what you can tell here is that I have a slab here, I have another slab, this is a column, and this is another column. The beam runs from here up to here, and because of the monolithic pouring of concrete, the beam, this is my rectangular beam, it's going to take some portion of the slab and some portion of the slab. It's going to have a flange. So what you can tell, it looks like a T. So this is called a T beam. And we also have L beams. So the designing process is a bit different when we consider a T beam or a L beam. And well, we'll have to find the effective flange width, the effective breadth of the flange. And this process, I did explain it in another video as per the Eurocode 2. It's not that difficult, it's actually very easy, but the process here takes some time. It is a bit different, but we will stick on designing a rectangular cross section. Right, so we move on and define some of the initial or some of the aspects of a cross section. Now I'm defining some of the terms. Here we have the breadth, so it's given as B. This is the breadth, okay, and the overall depth, okay, from the extreme top to the extreme bottom is the H. So this is the overall depth. But the depth from the extreme top to the center of the tension rebar is the effective depth. It's given as D. We have the effective depth of the compression reinforcement, and we have the effective cover to the reinforcement. Okay, so this is D is the effective D is the effective depth of the tension reinforcement. D prime is the effective depth of the compression reinforcement. Alright, so this is of course the tension reinforcement at the bottom, and this is the compression reinforcement. But if you don't have any compression reinforcement, then these are going to be hangers. And of course we have the concrete. So this is the concrete, and the grade goes from C25 to C50. And we have the shear links, also called the stirrups. So basically when we have a sagging moment, then this is the way how we tie the stirrups. But when we have like a case when we have a cantilever, that is a hogging moment, then we tighten this way. And basically this is because we don't want this to open up under tension. Alright, now we jump to our example. Now this example might take time because we'll be designing this beam entirely. We're gonna talk firstly about the bending moment. So we're designing the beam to resist the applied bending moment, and then we'll check the shear faults as well. So we'll be putting the links, and then finally we'll be checking we'll be going through the detailing. So the example here, this is a design example, and it really it doesn't really give you much. This is probably all what you need. The load on the beam, that's the live load and the dead load. And we have the materials, so this is the grade of concrete and this is the grade of steel. We have the effective span. What they say here is that the self weight as well of this beam is included in the dead load. So the dead load here includes the self weight of the beam. Now we have to design this beam, so we'll start from the scratch. So let's design this beam. So this is the first part of this video, the bending design, and we will have to select the trial section. We'll have to select the area of reinforcement for bending resistance, and then finally we'll be doing deflection check. And after the bending design, we'll go through the shear design and then detailing. So let's start the first part. Now the first step here is to determine the initial trial section. As I said, we go back to that deflection table, and since we are designing a beam, we say that it is highly stressed, and I'm going to take the ratio L over D is equal to 14. Okay, so my D from this ratio, I have the L, so my D is going to be 430, but I'm going to take my D to be 450, and that's fine. Also, we said if the D is 450, then the B is going to be a third or half of this. And if you just plug and check, you'll see that the B is 225, but I'm gonna take it as 300. This is totally fine. I can take it as 250, that's valid. I can take it as 300, that's also valid. But for my design process, or for my design problem, I'm gonna take these dimensions. Right, so I have defined the B and I have defined the D. I might go back and change this if this is required later on. We'll be checking all of this. Right, so the next thing that I have to define is the cover to the reinforcement, and we're starting with this equation. We have the C nominal, it is equal to C minimum plus the delta C deviation. Now the C deviation goes for the construction deviations, and it is normally taken as 10. Okay, so let's just keep this as a constant, so it is 10. The C minimum, that depends. So what kind of exposure class? So my beam, I'm assuming my beam to be XC1, so exposure class 1, that is a corrosion risk. I'm having a corrosion risk, and my structure is inside, so it is under dry condition. And that, if you check it from a table given by the Eurocode, you'll see that for exposure class 1, the minimum cover has to be 25. So this is just the minimum cover, not the nominal. And the nominal, just you add them up, right? So 25 plus 10 gives you 35 millimeter. So 35 is going to be my nominal cover to the reinforcement. Just to make this clear, when I say the nominal cover, it's from the extreme bottom to the face of the reinforcement. And of course here, I didn't really draw it, but we have the shear links here. So it is from the bottom to the face of the shear links. It is going to be 35. And also, the important thing here is that I'm gonna assume, I haven't yet determined whether I need compression reinforcement or not, but I'm assuming that if I be needing compression reinforcement, then I'm gonna give it an effective depth of 35. Okay, and if you just see, this beam gonna have sagging moment, and that means cracks will appear at the bottom. So I have to take care more for the bottom side, not the top side. This will be under compression, and as you can tell, this is the effective depth, so it is to the center of the compression reinforcement, but this is not yet. I mean, I'll have to calculate this. This is what I'll be doing next. So we just jump to our section. Now I'm gonna calculate the effective cover to the tension reinforcement, and that is giving as A, this letter. And to do so, well, we'll have to assume something. Now I haven't yet determined the rebar diameters, and I haven't yet determined as well the link's diameter. So I'm gonna assume my link's diameter to be 8 millimeter. That's something reasonable. So it's between 8, 10, maybe probably 12. And for the tension reinforcement, I'm gonna take it as 25, right? Sometimes it might be 25, it might be 20, it might be even less than this. But I'm gonna just assume it as this. So my A is going to be what? This distance, the 35 that we have already calculated, plus 8 for the shear links, and plus 25 divided by 2. It is given as 50. Now, why do I need the 50? It is because I need to calculate the overall depth, the edge. So simply, it is just the 430 that we have already determined plus 50 gives me 500. And that's it. Now, I'm gonna check something really quick. This is the fire resistance. If it's required for you to check the fire resistance of your beam, and well, I have to check this table. It's given as well by the Eurocode, and you only need the B and A. This is the effective cover to the tension reinforcement that we already have determined, and this is our B. Let's check it. Now, if I want my beam to resist the fire for 60 minutes, that's 1 hour, I'm gonna just check this. This is the 300, this is the B minimum, and the A is 25. So I'm having 300 and I have 50. So that tells me I am meeting the fire resistance requirements for 1 hour resistance. This is just a quick check. Now, I'm gonna move on and determine the total ultimate load at the moment. So, as we said, we need the beam. We already have the loads, okay? And that if we just draw the free body diagram, okay, and then, well, it's simply gonna look something like this. And then we take the ultimate design load combination, and we know that for the ultimate design, we take this partial factor of safety for the dead load, and this is for the live load. So just plug and check, you'll see that we have a total ultimate load of 70.5 kilonewton per meter. Now, simply find the bending moment, the maximum bending moment. It will occur at the midspan. So for a simple supported beam, it is W times L square over 8. So this is my maximum bending moment. And the first step that you do after finding the maximum bending moment is that you determine whether your section will be singly reinforced or doubly reinforced. And this is done by this K value, right? So K is given as M over BD cube, BD square FCK. We have everything that we need. The moment is due to the ultimate load. So this is our moment. We have the B 300, we have the D, and this is the grade of concrete. Now it comes out to be 0.175. We check it with the limit. Now the limit is given by the code to be 0.167. The K that we have determined is larger than the limit. That tells me that the beam has to be doubly reinforced. Now I can do something here. I can go back and change my depth and breadth as well. I can change the breadth or I can change the depth, but you can tell here that there's the square here. So if I'm gonna increase the depth, the K gonna reduce significantly, and that if I do so, then I can get a number less than this limit. So I will have to design my beam as a singly reinforced beam. But in this case, I'm fine with a K larger than the limit, but in this case I'll have to design my beam to be doubly reinforced instead of singly reinforced. Right, that's it for the K. Now once you have determined the K value, so it is 0.175, you're gonna need the okay, the area of compression reinforcement and the area of tension reinforcement. And of course you'll have to determine this one firstly, and secondly you can determine this one, because as you can see here, there's this compression reinforcement. You cannot determine this when you don't have the value of this. But before you just jump to that process, you need to check whether the compression reinforcement has yielded or not. And we do this by plug and check. This is something very simple. We have this d prime over d, and this ratio has to be less than 0.171. Again, this is given by the code. If this is true, if my d prime over d is less than this figure, then that tells me that the compression reinforcement has already yielded, so its value is going to be 0.87 fyk. So let's check it with our case. Now we have the d prime, it is 35, and we have the d, the effective depth to tension reinforcement. And just if you put this ratio here, you'll get 0.07. Now this figure is less than this figure. That tells me my compression reinforcement has yielded, and the F sub SC is equal to 0.87 fyk. So simply, just check this one here. If this is true, you just carry on, find the area of compression reinforcement, and then find the area of tension reinforcement. Simple as that. Now there is also another check, but it is for the compression reinforcement, whether it has yielded or not. But we don't have to consider this, we don't have to worry about this, and it's given as this ratio x over d. But since I'm putting the compression reinforcement, that ensures me I'm gonna have a ductile failure mode. A ductile failure means tension reinforcement yielded already, right? So we only check whether compression reinforcement has yielded or not, but we don't need to check whether our tension reinforcement has yielded or not. So let's look back at our trial section. Now I have the B, all right, I have the H, and I have the effective depth of the tension reinforcement, as well as for the compression reinforcement I have my effective cover to the tension reinforcement. And for now, that's it. This is my trial section, but remember, this is just the dimensions. I haven't yet determined the area of compression reinforcement and the area of tension reinforcement. I haven't yet gone through the shear links design, but hopefully this is what we're going to do next. But for now, I'm gonna just stop this video, and hopefully very soon I'll be uploading the next part of this problem, and we'll be going through the bending design as well as the deflection check. So till then, thank you very much for watching. I'll see you very soon.